Exponential and logistic functions. This is section 3.2 in your textbook if you're curious. So just a quick review. I'm sure you've talked about E in other classes, but E comes from taking the limit of this exponential equation over here. And as we get really, really big values of n, the whole function becomes closer and closer to being equal to 2.71828, etc. Usually we use just 2.718 as a good approximation, 2.72, somewhere in there. You'll get the same kind of ideas. We get exponential growth with E. You can also have exponential decay, depending on the value for this this piece of the exponent right here. So we're also going to be talking about modeling different equations today. So we need to remember not just the E stuff, which will come into play a little bit later, but some of the stuff we did before with the A times B to the X type stuff. So looking at the population of San Jose, we're going to try to see if we can come up with an exponential function to represent the population growth. All right, so since we're talking about population, I'm going to use P of t to represent our function. So P of t, and instead of using A as the initial value, I'm going to call that P sub O, so that's the population at year 0. And we're going to raise it or multiply it by B, our growth factor, raised to T, which we'll call the time in years. So we need to know our initial population, and we need to figure out what the growth rate is, and then we're going to express this as growth per year. So I'm going to give myself some room to work here. We have P of 0, which is going to be our P sub O, which is the 1990 data. So that's 7822224. And then we know that P of 6 is equal to the P sub O times B to the T, where T is 6, and that's equal to 838,744. So using this second equation here, we can solve for B. We're going to divide both sides by the P sub O. There, I jumped ahead. And then we need to take the 6th root, and luckily we don't need to worry about any negative roots here. So B is going to be equal to about 1.0117. So that makes the whole equation P of t is equal to P sub O times 1.0117 raised to t, which is the time in years. Sometimes we're given the rate of change or rate of growth or decay in terms of percent. Everything works the same way. Usually this is a population or maybe something else kind of in the social science area, number of bacteria, whatever. Initial population times 1 plus r, where r is the percentage rate, and it's going to be the decimal form of that. So instead of having a b value as our growth rate or growth factor, we have 100% plus the additional percent, or minus if it's a decay. So let's look at an example of that. So in order to solve a problem like this, where we're given information about a rate, we're given our initial, but we're asked when does it reach a certain level, You might remember that you can solve this with a logarithm. We can also solve it graphically, which is what we're going to do here, or I'll at least explain the process. We're going to write out the function, which I'm just going to jot down, so pause when I get to it. Notice that it's subtract because we're in a decline, and I use the decimal form, and then here's my initial, etc. If you plug this into a calculator into y equals, you should also plug in y equals 1 million to get a horizontal line right at that point, and I'll show you what that looks like. Okay, so I had to zoom really far out to show this graph, but I will zoom in a little bit so you can see what this looked like here. So the purple is the y equals 1 million. The red is the exponential function. We're finally getting closer. So this is going to be kind of difficult on your TI graphing calculators. So right here is where we start seeing, where we see our intersection at x equals 12.7. 1 million. So that's our answer. It takes 12.7 years.